This is the second part of the AnimatLab robot control video tutorial. In the first tutorial, I showed you how to set up the simulation of a robot arm to pick up a ball and drop it into a bin. Then, in the first part of the robot control tutorial, I discussed how the robotics framework operates and showed you how to set up the simulation to work within that framework. In this tutorial, we'll set up our hardware and make the robot perform the same movements that we configured in our simulation. Next, you'll need to open the Arbotix Fermata sketch in the Arduino application. Make sure you have the right COM serial port selected, and make sure your board is set to Arbotix, and that the programmer is set to AV-RISP MK2. Then finally, we'll be using the default baud rate of 115,200, which matches what we put into our simulation. However, you can use these different settings if you want to. You just have to make sure that what you put in the simulation file and what you upload onto your microcontroller match. Now we're ready to hit the upload button. Once it's done, you'll see done uploading, and you'll see here that the size of the sketch with no errors. And this lets you know that it's successfully uploaded the Arbotix Fermata sketch to our Arbotix controller. So now we're done with this. We have Fermata running on our controller so that we can talk to it. Now we need to go back to AnimatLab. First, let's set it up to collect some data. Select the robot data chart and add an axis. Then add each of our new control neurons to this axis. Let's verify that the end time of our chart is 6 seconds and that our simulation end time is at 6.2 seconds. If you don't have this set up to stop at a given time, then the simulation will run indefinitely. Next, for these tests, we want the robot to always reset to the same starting point each time. So let's go back to our servo part interfaces and set the reset to start position to true. If you set this to true, then please be aware that you'll need to pick up your robot off the ground until it has reset the positions of all its servos, or you could risk damaging the servo gears because it's moving quickly to set each servo back one at a time. After the servos are reset, you can then set it down for it to move. Now let's go ahead and export out our robot organisms control system. Go to the organisms node and right-click and select Export Robot Standalone Simulation. Make sure that we use the default physics engine for robotics. We'll keep binary types as it is, and in this instance we're using the Windows operating system. Hit OK, and it lets us know that it created the simulation file successfully. And we can see that we got a new standalone simulation file created. Now let's open up a command window and CD into the bin folder of AnimatLab. We can now run this simulation from the command line using the Animat simulator. We just need to specify the directory, the full path to where our simulation file is at. This will attempt to run our robot simulation for 6 seconds and produce the same type of behavior that we set up in our simulation. We can see that the robot went through the motions that we programmed for it, and if we look in our project directory, we can see that it dumped out the data that we asked it to collect in the robotdata.txt. Let's rename that file to robotdata_robot.txt. Then start the simulation and run it again. Now let's export out the data that was collected in our simulation. And we'll rename this Sim. Then let's start up Excel so that we can look at our different data. Now let's chart the TC position over time for both the simulation and the real robot. So we can see that it's quite close. However, there are some differences. For instance, if we zoom in, we can see that there's a slight delay here between when we command it to start moving and when it actually starts moving. So it starts moving at around 0.5. But we commanded it to start moving around 0.4. So there's about a 100 millisecond delay there. So let's try and account for this in the simulation. Let's go back and select the TC adapter. To try and deal with this type of issue, I have added a new feature to AnimatLab that lets you specify a delay buffer between inputs coming into an adapter and the output that's applied. This is controlled by the delay buffer interval. It's already set to 100 milliseconds, which is what we need, so we'll keep that default. However, if we want to try and make our simulation more closely match the real system, it's important that we only perform this delay on the simulation and not in the real system. The delay in the real system occurs due to the time it takes for a command to the servo to get processed and take effect. The delay buffer properly lets us control this. So the delay buffer mode is defaulted to no delay buffer. If you pull this down, you'll also see that you have options for delay in simulation only and delay buffer always on. We need to choose the delay in simulation only. This is controlled on an individual adapter basis because the delay for one interface may be different than the delay for a different one, and this gives you the fine control you need to deal with those differences. Now let's go through all of our motor adapters and set them to have a 100 millisecond delay in the simulation. Then let's re-export out our standalone simulation file. Now rerun the simulation. This time we can see that the simulation and the real system match much more closely. There are a couple of other important parameters that we should set within the simulation to make them more synchronized. These are found in the Robot Properties section of each adapter's property grid. The first of these is Robot I/O Scale. These properties will only be visible if you have a robot interface defined for your simulation. The first property is Robot I/O Scale. You may run into a situation where the motor output that's being produced doesn't quite match what is being produced by the simulation. If that happens, then you can use this Robot I/O Scale to slightly change the scaling of the output variable within the simulation only. This is to allow you to tweak the output to try and more closely match what the real motor is doing. Another important property is the sync with robot. When we configured our robot interface, we set a flag telling it to sync with the robot. When these two values are true during the simulation mode, the adapter will only update the source data when the sync update interval has expired. When you run the real robot, your motors will only be updated at some frequency determined by the hardware. In our case, we set our robot time step to 2 milliseconds, so all the motors will be updated every 2 milliseconds. However, the simulation steps at a much higher rate than this. In order for the simulation to more closely match the behavior of the real robot, we should only be updating the values for the motors at a similar pace. These properties allow you to control that. You can use the sync with robot flag of an adapter to turn this on or off for individual adapters, and then set the sync update interval to be what you need. For our case, we want to set this interval to be 2 milliseconds. Let's go through each of our adapters and set this value and then rerun the simulation. Now let's look at the CF position. Comparing the simulation output, we can see that it's fairly close. However, the final position of the parts are off by just a little bit. This is primarily due to the fact that we're using only velocity control here, and it will be difficult to eliminate that entirely using just this control system. We'll look in the Dynamixel USB control tutorial and show you how to use both position and velocity control to eliminate this issue. Next, let's go ahead and hook up the contact sensor in the gripper and get the robot to be able to actually pick stuff up. We need to hook up the contact sensor within the simulation to be driven by the real pressure sensor on the robot. To do this, we need to add a new analog input part to the Robotic controller. Let's call it L grip contact. We want to set the link part to be the left grip pad, and then set the linked property to be contact count. These two values control which property and part is updated with the transformed analog value. Next, set the pin to be 1, since that is where we connected our sensor to on our Arbotix board. Please note that the pin number shown here matches the analog pins for the Arduino, so it would be A0, A1, A2, not pin 27, pin 28. So you need to make sure of that. So one of the primary goals of the Robotix framework is to make the neural network be able to control both the simulation and the real robot seamlessly. To do that, we need to set up the I/O so that the network is not aware it is talking to the real hardware or the simulation. In this case, we're doing that by setting the same variable that the simulation monitored to detect when the gripper was closed, the contact count. We're simply driving it from the real pressure sensor now, instead of from the simulation. The analog input on Arduino boards uses 1023 for 5 volts and 0 for 0 volts. When there's no pressure on the sensor, we'll get a reading of around 1023, but as pressure is applied, that number will drop down to a low of around 300. We want to translate these fixed point values into binary value where 1 is contact and 0 is no contact. To do this, let's use a sigmoidal gain function. Set the X offset to be 700, the Y offset to be 1, the amplitude to be -1, and then set our upper limit to be 1023. Now when we get analog values above 700, it will set the contact count property of the sensor to be 0. But when we get analog values below 700, it will set the contact count to be 1. Now let's add contact count to our chart so we can see the data from it. Then export out our standalone simulation. And then rerun the simulation. This time the robot does what the simulation showed. It goes over, picks up our ball, and moves it back to the bowl and then drops it in. If we pull up the data chart on the contact count, we can see that it was set to 1 when the gripper applied enough pressure to the ball. In this tutorial, I've demonstrated how to add a robotic interface to your simulation to control the movements of the real robot using the same neural network from your simulated system without having to write a single line of code. One of the main goals of the robotics framework for AnimatLab is to make it very easy to build neural controls for robotic systems using off-the-shelf components. In future tutorials, we'll continue building on this robot to add to its functionality.